Hello, everyone. This is our third lecture. Um, Today's lecture is on chapter 2. We're going to talk about displacement, velocity, and acceleration. And then we're going to cover a bunch of problems in one-dimensional motion with constant acceleration and free fall. So the first half of this lecture is going to be a lot more math. I'm just going to derive and talk about displacement, velocity, and acceleration, including what those terms mean. And then we'll get into the problems. And the problems I'm hoping will be interesting and kind of fun. And hopefully I'll show you how to, an algorithm, basically a series of steps to follow anytime you have a constant acceleration or free fall problem. Free fall, it turns out, is a constant acceleration with a special acceleration, which is the acceleration due to gravity. So in this chapter, we're, for the first time, introducing the key concepts of acceleration, velocity, and displacement. And really, this is going to be the core of everything we do, because everything we do is based on forces, and force is F equals ma, which is mass times acceleration. So in general, a force will give us an acceleration. In this course, we're going to consider, for the most part, only forces that are constant. So we need to talk about how we mathematically describe constant acceleration and how to derive the equation for displacement and velocity from acceleration. So let's start with displacement. Displacement is pretty easy to understand. If I were to start walking, right? So I walk some distance, and let's say I walk 10 meters to the right. I would call this x initial and x final. The little zero subscript means that time zero. So my displacement is my delta x or delta y or delta z or delta whatever you want is always final minus initial, okay? And so in this case, my final would be 10 and my initial would be 0. So this would equal 10 meters. I would have a displacement of 10 meters. Obviously, the initial doesn't have to be 0. I could have started at 9 and walked to 19 meters, whatever. But when we talk about displacement, what we mean is we mean the change of distance. And that is always some final minus some initial. And keep in mind that here, x can be whatever coordinate we're talking about. We might be talking about z, we might be talking about x, we might be talking about y, okay? But as we derive these equations, I'm going to use x. In particular, remember that these could also be y. I could be talking about going up in the air, okay? But the main point here is that you have to choose a 0 point, a point where you're measuring from. And that's usually your x naught, although it could be, in a weird case, it could actually have a value. So from that, we need to talk about velocity. And velocity is how fast your speed changes, or how fast your position changes, I should say, not your speed. One really important point, I want you guys to get away from using the term speed. Speed in physics doesn't really mean anything. It's essentially the magnitude of the velocity, but velocity is a vector. In fact, our displacement, I really should write as a vector, because we have to define direction. So our displacement vector, our x vector, would have magnitude and direction. Velocity also has magnitude and direction. Speed is a scalar. It's just saying, I could say that I was traveling at 30 miles per hour, which sounds like it has vector quantity, but it's not. If I said I was traveling 30 miles per hour to the east, that would be a vector quantity and that would be velocity. But speed's just a scalar. It's just the magnitude of velocity, and it doesn't tell us really much of anything, so we don't use it. Your book talks a little bit about it. I don't think it's really worth mentioning. It's just an imprecise way that we usually refer to velocity as your speed, and we want to be more precise as scientists. And the precise term is either average velocity or instantaneous velocity, and we'll talk about the difference between those. So your average velocity, your change in velocity average, is simply the change in your displacement over the change in your time. So what that means is if I take some final position minus some initial position over some final time minus some initial time, I would get an average velocity for that time period or over that distance. So for example, I could go from 0 to 10 meters, and I could do that in 2 seconds, okay? And so here, my initial position was 0, my final is 10, my initial time is 0, and my final time is 2 seconds, and I'll put units on here. So my average velocity in that time is, and I really probably shouldn't write a delta here, sorry. It's not really a delta. A delta is a change. So my average would be 10 minus 0 over 2 minus 0, or obviously 5. The top was in meters, the bottom was in seconds. 5 meters per second. We'll talk a little bit later about graphically what average means, but that's it. That's all you need to know, is your average velocity is your change in position over your change in time in some interval. So most of the time, when we talk about velocity in this class, we are actually talking about instantaneous velocity. And the difference between average and instantaneous is a particular time. You say a time of 1.001 seconds. What is the velocity of a particle at that time? That's your instantaneous velocity. And we know how to do this. In fact, how we do this is instantaneous velocity, okay, is still this delta x over delta t, except now these become infinitesimals. And we'll graph this in a second to show this. But what happens when you let delta x go essentially to 0 and delta t essentially go to 0? Delta t becomes a moment in time, and so we get a change. We know how to do that. We take the limit as delta t goes to 0 of delta x over delta t, and that is actually a derivative. That is dx dt. Okay, so that is the change of position over the change of time as a derivative. So for instance, I might have a position function that is simply 2t, right? And if I want to know the instantaneous velocity, I have to specify a time. So let's say the instantaneous velocity at, I don't know, 4 seconds. Well, what is the derivative of this function of x, which I should really write, sorry, I'm being imprecise as well. I should really write this as a function of t. Then I take the function with respect to t. And that's obviously just t. If you take the derivative, this just becomes 2, and it becomes a constant 2 meters per second. That's easy and obvious, right? And so at any time, not just at 4 seconds, it's 2. So let's do a better one, okay? Let's do another function. What if our position function was given by 4t squared minus 3t plus 2, okay? And I want to know now the instantaneous velocity when t is equal to 2 seconds, okay? And so if I take d of x of t with respect to time, I get the 2 comes down in front, and I get 8t. This t goes away, so I get minus 3, and the 2 is a constant, so it doesn't appear. If I then put in t is equal to 2, I see that I get 2 times 8 is 16 minus 3, I get 13 meters per second, okay? Now, at time t is equal to 0, what is my instantaneous velocity? It's minus 3, because t would be 0, I would get minus 3 meters per second. And what that means is, if I graph this as a function of time, velocity versus time, at time 2, 1, and 0, my velocity here is actually negative 3, and here it's 13. And I know that's not to scale, but essentially somewhere my function is a line, obviously, it's a linear function, but somewhere my velocity changes to negative. So what that means is my particle is initially traveling this way, and it stops and it begins to travel in the positive direction, okay? And we could figure out what that is, but we could set this equal to 0, and we'd find that it's at a time of 3/8, which is fine, but I don't care about that so much. What I care about is this idea here, that instantaneous velocity is actually a derivative. It's the limit as delta t goes to 0, and that's the derivative. So out of all of this, what we come up with is that the instantaneous velocity, or the velocity that we usually talk about, is dx dt. That's all you need to know. I guarantee you that I will never probably, I mean, I might ask on a quiz or something for average velocity, because average velocity doesn't mean a whole lot. Let me draw a quick graph on a new slide. So let's say we have a velocity and we have a position. So this is going to be x versus t, and this is going to be v versus t, okay? And let's say my position function is given by, I'm going to give you something linear, is given by x of t plus 12, right? So as t increases, when t is 0, we're at 12, and as t increases, this is going to shoot up, right? I'm sorry, not x of t, 2t, 2t plus 12. So this would be 14, this would be 16, this would be 18, right? So at time of 1, if you put that in, okay, you would get something that looks like this. Now, if I were to take between position 1 and position 2, the value of x, and the value of x at 1 and the value of x at 2, so x at 1 and x at 2, x at 1 is 14, x at 2 is 16, and the change of time, so t1 is 1 and t2 is 2. So the average velocity is 16 minus 14 over 2 minus 1, or this would be 2 over 1, which is 2 meters per second. That's my average change in position over time. Not too hard to figure out, right? That's because if I take the slope of this, right, the slope of this linear line is y over x, which is x over t, which is my average velocity, is my change of x over my change of t. Just like a slope is the rise over run, it's the change of y over the change of x. On my graph, my y is x and my x is t, right? So that's what the average is. But at any point, the slope at any point is actually the instantaneous. And so here, what I could do is I could take the derivative of this, which is obviously 2, and I would know that the slope at any point here is 2. And what my velocity versus time graph is going to look like for this particular function is it's going to be a flat constant line because I have constant velocity. Now, I could have something weird that looks like some exponential maybe, right, that does this, and my slope is generally increasing, right? So my v of t graph here, my slope is essentially 0. And as it goes, my slope at each point is going to be, it's the line that's tangent to each point, and eventually it's going to get infinite. So my slope is going to be increasing pretty much the same way. It's going to start from 0 and it's going to rise and eventually shoot up. My velocity is going to increase. So we know that an exponential function, if x was equal to e of t, which is what this is saying, then the derivative of this is dx dt. The derivative of that is, again, e of t. So we know that the velocity would increase the same way. The instantaneous velocity is the derivative, and the derivative is a rate of change. It's the change of position with time. On an x of t graph, your slope, if you took it over several points, would be an average. But your slope at any particular point, if you specify a particular time, that slope is your instantaneous velocity, okay? Now, everything we've just done, we can do again for acceleration. And acceleration, I talked a little bit in the other video about this, but acceleration is a little bit harder for a lot of people to understand. You might have it down. Some people, it's really hard for you to understand. But basically, your acceleration is how fast your speed is changing. If something's slowly sliding down a hill faster and faster, it has a slow acceleration. If something's speeding up, like taking off in a car on a dragster, super fast, it has a really quick acceleration because it's getting up to speed super fast. Another example, if you've ever flown on a plane, when you take off, you have super fast acceleration in that plane. And you take off from the runway and you lift off into the air. And then once you get in the air and you reach your flying speed, your acceleration goes to 0 and your speed is still really fast. You're flying at a really fast 300 miles per hour or whatever your plane's flying at, but it's flying at a constant velocity. Its speed isn't changing. And if your velocity isn't changing, your acceleration is 0. It's actually Newton's laws that we'll talk about on Monday, but the acceleration, the average acceleration, just like the average velocity, is the change of velocity over the change of time. And so as you get faster and faster, this is your final speed at some time interval minus your initial speed over your final time minus your initial time. I could do an example for this. I'm not going to. I think you all get that. And then your instantaneous is, again, when we take the limit as delta t goes to 0 of delta v over delta t, that is a derivative, and that is the change of velocity over the change of time. Now, we already know the velocity is the change of position, so this is something called the second derivative of the position function, and this is really v of t. I should write that to be specific. But, so the velocity is the first derivative. It's the rate of change of the position. And the acceleration is the rate of change of the velocity, or the second derivative of the position. It's the rate of change of the rate of change of the position function. And generally, we don't often draw a t-graph, but let's say your velocity, as I said with the plane, your velocity starts off and it increases really fast and then it dies out. We could draw an a of t graph, and what this is going to look like is it's actually going to be really high at first, and it's going to drop to essentially 0 where it flattens out, right? So your acceleration is very fast, really, really positive at first, and it decreases and decreases. Just like the slope of this line is decreasing with time until it becomes flat. A slope that's horizontal is 0. That's because the changeover, the slope is 0, essentially, okay? Because there is no change in v here. This v and this v are going to be the same, so you get a slope of 0. That's easy to understand. That's all there is to this whole instant versus average stuff that the book spends the first 3 sections on, or whatever it is. And I've kind of jumped ahead on the PowerPoint here, and that's okay. But the thing that I really want to say is, remember that A is the time derivative of the velocity, or the second derivative of the position, and V is the time derivative of the position. And then the other thing to remember is that when we say delta x, we mean x final minus x initial. If we say delta time, we mean time final minus time initial. If we say delta v, we mean v final minus v initial. And the last thing to remember, or last two really, is that when we say x, we really mean x can be y or z or whatever coordinate we want, and that speed is just a scalar magnitude, okay? And I guess if you want an average, v average is change of position over change of time, and a average is change of velocity over change of time. Okay, so that's all there is to this stuff. It's not really something we'll test on. We really need to set this up so that we can derive the equations of constant acceleration. And that's what we're going to talk about next. I already covered the graphs that I wanted to cover here. We'll talk more about graphs at the end. But if we have motion with constant acceleration, okay, we know already that A was dv of t dt. We can take this equation and we can actually solve it as a couple of differentials. All I did was I multiplied both sides by dt. If I take the integral, and I have to go from v initial to v final, but I'm really going to call v final v for clarity. And here I'm going to go time initial, which I'm going to say is 0, to t final, which I'm going to say is just t. And yeah, they have the same variable. It's okay that they have the same variable. If I do this, these integrals, when I solve them, I get v minus v naught. There's nothing in front of the infinitesimal, the dv here. Therefore, it goes up and I get a v. I go from v naught to v final. So I get this. Here, and I am going to leave this as v final, but I'm going to turn it back into a v in a second, and you'll see why. So here, I get a of t, right, from t initial to t final. And I really should have written that one this way, but where this is 0. So what this becomes is this becomes v final minus v initial is equal to at. And that's actually our first equation for constant acceleration, motion with constant acceleration. Now, this equation actually is in a particular direction. So we could say it's v final of x minus v final of y, or v initial of x. Sorry, my tongue is not working. V final of x minus v initial of x is equal to the acceleration in the x direction times time. And remember what I said, the time is really an interval, but because we're assuming that we start at a time of 0, we just write t. It's how your book does it. It's how every physics book does it. But you need to remember it's actually an interval there. Okay, this could also be y. So this also gives us v final of y minus v initial of y is equal to a y t, and v final of z minus v initial of z is equal to AZ t. We can have this equation in any coordinate that we want if we have constant acceleration in that coordinate. And we're going to write this further for the derivation. We're going to write this as v initial plus AT. What I did was I moved the v initial term over. I'm going to use this in a minute. But super simple, super easy integrals to do. But out of that, we get this, and we're going to use this over and over again. This is going to be with us for the rest of the course. What that's saying is that your final speed is equal to your initial speed plus whatever your acceleration is times time. Let's look at these units. Meters per second, meters per second, meters per second squared times seconds, which this is also meters per second. Now, why is this meter per second squared? Because we said that v was x over t, and that's obviously meters per second. And we said further that a was v over t, which is meters per second, or meters per second squared. Those are our units. Just know them. Acceleration has units of meters per second squared. Velocity has units of meters per second. And displacement has units of meters. Okay, let's continue our derivation, okay? We just found that v final was equal to v initial plus AT. And we know that v is dx dt. So doing the same thing we just did, we're going to have dx is equal to v dt, or v naught plus AT dt. And if we go from x initial to x final, and we go from t initial, which is again 0, to t again, t final, which is again t, what we get here is we get x final minus x initial. This just comes up as an x, and we're going from x final, x initial. This, however, one power of t comes up, this power increases. So this becomes v naught of t, or times t, plus the power of t goes up to 2, and you divide by the new power. And it goes from 0 to t. So t, we will get v naught t plus AT squared over 2 from t to 0. But that would just, the 0 doesn't matter at all. This, again, if I put a little x and I put a little x, okay, this again, you could have this same equation in y and in z, in whatever coordinate system you have. This is our second equation. I'm going to put these all together for you later. We're going to have one page in 2 slides from now. We're going to have one page that has all the equations for you. Actually for projectile motion, but I'm going to do it first in general. Actually, I'll do that now. So let me do a new slide, and let's derive some of these things. Okay, so what we said already was that we had v final was equal to v initial plus AT. And secondly, we have x final minus x initial is equal to v naught times t plus AT squared over 2. Remember that this is the acceleration in the x direction. This is the final velocity in the x, the initial, this is the initial. So there's a few things we can do to manipulate this around, right? We can solve this for AT. AT is equal to v final minus v initial. Let's plug that in here, okay? And what we get is we get that x final minus x initial is equal to v naught t plus AT times t over 2, which is v naught of t plus v final minus v initial times t over 2, okay? And you can see here that what these end up being is v naught of t minus v naught of t to the half plus v final of t to the half. And this leads to a second equation, which is x final minus x initial. If I subtract half of a v naught times t here, I get v final plus v initial over half times t. That is our second equation. Another thing I can do is I can solve this for V naught. And if I solve it for V naught, I get V final minus AT. And if I look at this, do I want to do that way? No. What I want to do is something a little bit different. If I square this, so if I square V naught squared is V naught plus AT squared, and that becomes V naught squared plus 2 V naught times A times T plus A squared T squared, okay? Now, what I want to do is I want to solve V final squared minus V initial squared. And what that will give me is that'll give me all this. So I'll get V naught squared plus 2 V naught AT plus A squared T squared, and then minus another V naught squared. And here these cancel. And so what I get is I get that V final squared minus V initial squared is equal to 2 V naught. Actually, let me back that up a minute. 2 times A times V naught of T plus, if I pull out a 2A from here, I would have to multiply this by A T squared over 2. And I can see right here that this is my X final minus X initial. So what this gives me is V naught squared minus V naught initial is 2A times X final minus X initial. I'm going to write things clearer in a minute, but we've now derived 4 equations. And what those are I'm going to write them like this. X final minus X initial is equal to V naught of X times T plus A T squared over 2. V final is equal to V initial plus AT. X final minus X initial is equal to V final plus V initial over 2 times T. And lastly, we have V final squared minus V initial squared. Keep in mind these are all X's. I don't want to write it on everything, but everything here is an X, is equal to 2A times X final minus X initial. These are the 4 constant acceleration equations. If you really wanted to, you could solve this for V naught of X and shove it in here, and you get another equation. No one does that. I don't know why your book even suggests it, but it is true. It would work. But these are the constant acceleration equations. These are given, basically they're derived for you in section 23, or section 2.4. So if you look at section 2.4, they are derived for you. Know them, get to know them. There's a few really special things about these. If we look at this, let's start here. Notice there's no time. There's no t in this equation. In this equation, there's no a, okay? In this equation, there's no x. And in this equation, there's no v final. And what we're gonna find is that when we're doing problems involving constant acceleration, we're gonna figure out what our variables are, and then we're gonna need equations to relate those variables. And these are the only equations we have. You don't need to memorize them. You can look them up, but you can also derive them. They're, as you just saw, they're really fast to derive. You could derive these while you're taking your MCAT if you needed them. You can derive them in the middle of a test if you really needed them, just by remembering A is dv dt and V is dx dt, and then just solving those integrals. They're simple integrals. So I wouldn't necessarily try to remember them. You'll remember them eventually from doing enough problems. You might even remember them by the end of this lecture, because we're going to do a bunch of problems in this lecture. That's why I'm kind of hurrying through this. But we're going to talk about that algorithm in a minute. Before I do, I want to talk about a special case that we're going to come up with of these equations for Monday. And that's the case when you have projectile motion. So in projectile motion, what you have is you have an object that goes like this, okay? And we break this motion up into, so it starts off with some v initial, which has a magnitude and some angle. And so what we do in these problems is we make an x side and a y side. And we note that in the x direction, I should do this, there is v naught in the x and there is v naught in the y. And how you find those, so v naught in the x is whatever your magnitude of the initial velocity is times cosine of the angle, and whatever the magnitude times sine of the angle, those give you your initial. But everything else that we do is we write down the variables that appear in those equations. V naught of x, v final of x, a of x, and t. And here we write down y naught and y final, and v naught of y, and v final of y, and a of y, and t. And now here we need to stop for a minute and notice something. So for the most part, well, before I do anything else, I need to note that y going up is positive. And the only acceleration in this problem is in the y direction, and it points downward, and that is g, okay? And this is going to come up as a problem that we're going to see in a minute, but the acceleration is negative g. It's negative because it's pointing downward. Make sure you understand that this is true. And we'll do that when we do these equations. So initially here, if we start at the origin, both x initial and y initial are 0. I don't know what x final or y final is. We'll talk about that as we do problems. This is v naught cos theta. This is v naught sine theta, right? But now I want to get to the equations really fast. Since a of x is 0, remember our first equation said v final was v initial plus a to the t. So in x, since acceleration is 0, that tells us that the velocity in the x direction never changes. That means that these are exactly the same. These are both just v of x. Because there's no acceleration in projectile motion. In free fall is actually a one-dimensional case of projectile motion. It's projectile motion where there's no x motion at all is what free fall is. So we have that. For y though, v final of y is going to be equal to v initial of y plus a of y times t. Now a of y though is a negative, so what you get is v initial of y minus gt. This is where a lot of people get messed up, okay? They think that what this equation really says is v is equal to v naught minus at, and then they want to shove in minus g for a like that, and they get v final is equal to v initial plus gt. Don't do that. When you solve these equations, plug in for a minus g. It's minus because it points downward. We're going to have some problems towards the end of this where we have free fall, where they're falling. We're going to have a couple problems with constant acceleration where we have stuff that's actually moving in a negative direction. We have to learn to be really careful with our signs. As I said, this is 0. Since this is 0, if we go back and look, if this is 0, we get x final minus x initial is v naught of x times t. This says v final is equal to v initial x. Here, since v final and v initial are the same, we just get v times t, which is the same as that equation. And this equation is 0. It says that v final squared is equal to v initial squared in x if a of x is 0. That just tells us the same thing. So really, the only thing we have here is that x final minus x initial is equal to v of x times t. Those are the only two equations you have if you have no acceleration. These are constant velocity. In the y, you go back and you replace a with minus g, minus g, minus g in all those equations. And we'll see that soon, but they end up being this. So you have for y, since a is minus g, and I plugged in here for everywhere that I had just a x value that could be any coordinate, I've plugged in the y's. And you can see that your acceleration is now a negative g, negative g, negative g. Okay, so these are the correct equations for projectile motion, which we'll study when we talk about chapter 4. These are the correct equations for the x direction when we talk about projectile motion and free fall motion. These we're going to use later when we do free fall. And then this part we'll talk about when we do projectile motion. Often in projectile motion, you're given the initial velocity vector and the angle it makes. So you have to figure out what these initial values are. And then you can figure out the magnitude of it if you aren't given it and you need to figure it out. We'll talk about that on Monday, not today. And that's it. That's all the math we need right there on that page, to be honest with you. It's not too tough. It might look tough and scary right now. Once you do 4 or 5 of these problems, you're going to have it down and you'll breeze through these problems easy. However, I'm going to teach you a way to do these problems where you're going to need to use your brain the least amount. You're not going to need to basically think too hard. The hard part of these problems is going to be the first step, and we need to talk about that. So an algorithm for solving a constant acceleration equation, the first thing you do, you might have more than one, and we'll talk about that later when we do, but the first thing you do is just write down your variables. Write these down. You may write them you may end up writing them more than once, but because you may have different times. But essentially, this is at the start of the problem what these values are. And if you had y, you would similarly make a column for y, and you might call these x. Okay, that's the first thing you need to do. Just write down, list those variables, and then try to fill them in. See if you can fill them in. We'll do this for every problem, so hopefully you'll get it. But you list your variables. You also are going to need to include variables that you're assumed to know. And that means things like, if we say that the object starts from rest, you would know that if it starts from rest, okay, you know that the initial velocity is 0. You're generally going to have to assume where the initial x is. That's kind of up to you in a way. If, let's say it has constant velocity, well, the acceleration is the change in velocity. If the velocity is not changing, you know this is 0, okay? So the next thing you do is, and I don't care, this isn't as important, I generally put a question mark or I box whatever I need. In general, in these problems, you're going to end up not knowing 2, maybe 3 of these things. But we choose the appropriate equations once we have our variables in front of us. And you'll see how that works. I'll do that each time. But again, what I mean by choosing appropriate equations is each of the equations is missing something, right? So if I know x final and I know x initial and I know a and I know b initial, right? But I don't know b final, I don't know time, and those are the things I want to solve for. The first thing I look at is I can't use this equation because, well, I can. There is no b final. I don't need to solve for it right away. I can solve this equation for time. I can't use this equation because it has both v final and time. So immediately that one's out because it's got two unknowns. I can't solve it. I can solve, or I can't solve this one because it's got v final and it's got time. So that equation's out. The last equation doesn't have time, so I can use this to find v final, or I could use this to find time. It's really up to you. And we're going to go through that for each problem that we do. We're going to do like 9 problems in a minute. But essentially, whatever you don't have, but you know what you're looking for, whatever you're looking for, you can go to the appropriate equation just because you're not going to be able to solve an equation that you have more than one unknown anyway. So here's a bit of advice if you're actually stuck on these problems. These problems are usually, or are basically trying to get information. You're trying to fill in this block, right? And if you have at least 2 unknowns, maybe I could try to solve for time, but it might be easier just to solve for v final. Or what if this were, what if I was solving for, I didn't know, let's say I didn't know, let's say I was trying to find x final. I knew v final, I knew v initial, I knew a, I knew x naught. I could solve for t really easily right here. And even if I wasn't asked for the time, it might be easier to solve for t here and then go from there for some reason, okay? Solve for t and then plug it in here to get x, whatever. You'll see that. There's also no right path. Often there'll be 2 or 3 different equations or 3 different ways to solve one of these problems based on which variable you start solving for first. But my recommendation to you is if you don't see how to solve for the first variable you're trying to solve, go ahead and try to solve for another variable that you don't know, even if you're not asked for it, because it's often easier to solve for one of the other equations. And once you have it, you have more information, and more information makes everything easier, right? And on an exam, I know it's mean of me, but sometimes I'll ask you for the hard variables first, but you can go ahead and skip ahead and solve the next part for the easy. You'll see that. We'll talk more about that when we talk about practice exams. But anyway, I honestly feel like it's much easier to learn by doing problems. So that's what we're going to do. I'm going to take you through as many problems as I can. Basically, I'm going to take you through all the variations I can think of. There are a few variations we're not going to do, but you'll see them in homework or practice problems. The nice thing about constant acceleration and free fall problems is there's only so many types of problems. They are a limited class of problems, and you'll see that. So basically, once you've done 7 or 8 different problems in them, you've solved everything. You've seen every variation on the problem. So let's get started. Our first constant velocity. Our first problem is constant velocity. So what that's saying, what this immediately says, you need to highlight this. Anytime you see constant velocity, that means a is 0, okay? Just before we do anything else, make sure that you understand that always means constant. Now, before we even think about this problem, we know that this is a constant acceleration or constant velocity problem. We can write down our set of variables, and I'm going to use x here. Something that we didn't talk about, but we will in a second, or we will right now. It's sometimes helpful to draw a picture. Sometimes it's not. I'm not going to require you guys to on an exam, but sometimes it's helpful as you do a problem to draw. I cannot do physics without drawing. I have to doodle, I have to make a little picture. So I'm going to draw a picture while I do each problem of what I kind of see going on. And I'm going to label some variables on it. And you'll see how it can be helpful. So I have a motorcycle that's moving with constant velocity, 22 meters per second. And I'm asked to find how long in seconds will it take to travel 664 meters. So I know that I have a motorcycle. That's my little stupid motorcycle. And it's going to go a distance of 664 meters. And I know that initially it has a velocity of 22 meters per second. And I know that its final velocity is also 22 meters per second. As I look at this drawing, I'm going to assume this is 0 and this is x final. So x initial is 0 and x final is 664 meters. That's because it told me that it traveled a distance. It told me that delta x was 664 meters. The constant velocity told me that the acceleration was 0. So now at this step, I put in my variables. I know this is 0 from constant velocity, okay? I know that both of these are 22 meters per second. I know that this is 0, and I know that this is 664 meters. And the only thing left that I have to solve for is time, okay? So now I'm gonna go back and I'm gonna look at these and I'm gonna look for time. Well, it turns out that I have a bunch of them. Can't use this, this isn't gonna give me time. So this one right here won't work, but this one would, and this one would, and this one would. And really, you could use any of them that you want. I'm going to use these two, but you'll see that they're really the same. So I have V final is equal to V initial plus a T, right? This doesn't help me because it's 0. So that doesn't work. How about X final minus X initial is V final plus V initial over 2 times T. That I can solve for T. V final and V initial are just V. I'm going to call these V. So 2V over 2 is just V. And what this says is that T is X final minus X initial over V. I know that X initial is 0, so this is really just X final over V, obviously, which would be 664 divided by 22. And I have my calculator handy. 664 divided by 22 is 30.2 seconds. Okay. Another way I could have done this, though, is I have that final top equation says V initial times T plus a T squared over 2. And this term goes away because there's 0. But this is exactly what I found here. If I solve this for T by dividing through by V naught, I get the same equation that I got up there. They're all the same. It will give me the same amount of time. Yes, this is a super, super silly, easy problem, but what we're illustrating here is our algorithm. And our algorithm is just make a list of these 6 variables for every point in the problem that you care about. We'll talk about that because we're going to have some times where we need to figure things out. And we have more than one time to worry about, so you might need to make this list multiple times throughout the problem. But we'll talk about that. So write those 6 things down and then try to fill them in like it's a crossword puzzle or Sudoku or a game that you're playing on your phone. See if you can find X naught. See if you can find X final in the problem statement. This told me that A was 0. It also told me that V final and V initial were 22 meters per second. This told me that I was looking for time, and this told me that X final was 664 meters, okay? And then once I have these, I know that I need time. And you can box this or star it or highlight it. You then go back knowing that you have everything but time. I can say that I have X final, X initial, V final, V initial, and A, and I can look at these and see which one I could solve to get time. And that's all you do on these problems, except when they get more complicated, which we'll talk about soon. So yeah, this was a silly problem. Let's do something a little harder. We're gonna have the previous motorcycle is capable of constant acceleration of 14.5 meters per second squared. If it starts from rest, how fast will it be traveling when it reaches 25 meters from the start? So again, I'm going to make a drawing. This is my motorcycle, and when it reaches 25 meters, I want to know what V is when it's at 25 meters. And I know that V initial is 0, and I don't know why I drew that. I know that X initial is 0. I'm choosing that. And I know that the whole time it has an acceleration of 14.5 meters per second. So let's write this. V initial, V final, A, T. And if I ask you on an exam, usually the first thing I'll ask you for in these types of problems is list the variables for me. If you don't know them, it's okay. I want you to list the ones you know and put a question mark or a box on the ones that you don't, that you're trying to solve. Now, what do we know? We know X initial, it's 0. We usually can choose that to be 0. We're choosing it to be 0. We got the 25 meters as X final from the problem. It's asking us when it reaches X equal to 25 meters, how fast will it be going? The fact that it started from rest tells us that the initial velocity was 0 meters per second. We want this, so big star right here. That's what we're looking for. That's the question that we're trying to answer. And we know this is 14.5 meters per second squared. We don't have this. We don't need this. But we may solve for it to make it easier in some problems, even though we don't have it and we don't need it. So now, knowing this, we need to find V final. And we have a couple of equations. V initial plus AT. We don't know T. The other one that you almost always will go to is 2A X final minus X initial. Do we have everything in this except V final, which is what we want to solve for? Yeah, we know this is 0. We know A, we know X final, we know X initial. So V final squared is 2A X final minus X initial. X initial is 0. If I take the square root of both sides, what I get is V final is plus or minus. And in this case, we're going to choose plus because we know it's accelerating this way. And therefore, V final is going to be positive this way, which we're going to assume to the right is the positive direction most of the time, unless we have some weird reason for not. So choose the plus here. So V final is 2 times 14.5 times 25. And that answer is 2 times 14.5 times 25. 725 is 26.93, or 26.9 meters per second. And that is our answer. Okay. Pretty easy, right? We're choosing the positive there. You should never get a negative sign under your square root. If you have a negative sign, you've got something messed up. But let's go back and look at something. We knew that X final minus X initial was V naught T plus AT squared over 2. This is 0 and this is 0. So we have that X final is AT squared over 2. If I solve this for T, what I get is 2X final over A square rooted. 2 times 25 divided by 14.5, take the square root. Square root of that is 1.86 seconds. 86 seconds. And so I didn't want it, but I can solve for it. And then if I put that into here, I can get that V final is V initial plus AT, which is 0 plus 14.5 times 1.86. and that'd better match. So 14.5 times 1.86, I get 26.97. Slightly off because I rounded. When I got my B final, I rounded my square root. It's going to be slightly off. It's okay if it's slightly off, they should be close. In this case, they're a bit off, and that's because of rounding when I took the square root of time, which is okay. Like I said, I care more about how you go about it, and as you can see here, there were two ways to solve this. You could have found time and then used time to find B final. It's faster to use B final squared minus B initial squared is equal to A x final minus x initial. But I wouldn't be upset if you solved it the longer way. It just, sometimes it's intuition, sometimes it's habit that you have equations that you like. And it's okay. However you want to solve it, if you get there, you get there. Sometimes it's easier to get time. So now we have a kind of fun problem. This is another problem. In this problem, we have a semi-truck that's traveling with some initial velocity. So in the first problem, we had constant velocity. In the second problem, we had starting from rest. In this problem, we have a truck that's already traveling at 12 meters per second, and it decelerates. Now, deceleration means negative acceleration. It just means that A has a negative sign on it. We'll talk about that when we write it down our terms. We want to know how far it travels from the position where it begins to hit its brakes until it comes to rest. That's telling us that our final velocity is 0, okay? And then we want to know the time. So what we have is we have a semi-truck, and forgive my drawings, okay? It hits its brakes, and so it has an acceleration that way as its x final minus x initial, okay? And this way is going to be positive. So its acceleration is a deceleration. It's trying to stop. And we know that x initial is 0 and b initial is 12 meters per second. We know that A is negative 22, negative because it's a deceleration. And we know that B final is 0. We don't know what X final is. And we don't know what T is. So X initial, X final, V initial, V final, A and T. And we're actually going to be asked for both of them. We want to know how far it travels. So we want to know what X final is, and we want to know how long it takes to come to rest. So X initial is 0, we chose that. V initial is 12 meters per second. V final is 0. A is negative 22 meters per second squared, negative because it's deceleration, it's coming to a stop. We don't know, and we don't know. So we have a lot of different things that we can do to solve for this. I'm going to solve for time first because the simplest equation we have is this one. And we can solve this one for time really easily because that is 0. So what we get is we get V initial is A T with a negative sign, but A is negative. So what this becomes, we're solving for T. T is V initial over negative A, which is 12 over negative 22, or 12 over 22. 12 over 22 is 5.45 seconds, okay? 0.545 seconds. That's our time. So our time is 0.545 seconds. It's actually a repeating decimal. That's fine, close enough. Now I want to know what X final is, and I have the time. I have V initial, so I could use X final minus X initial is V initial T plus A T squared over 2. I don't really want to do that though. What I would rather use is V final squared minus V initial squared is 2A X final minus X initial. I know that's 0. I'm solving this for X final. I know that V final is 0. So X final, if I divide through by 2a, is negative V naught squared over 2a. But remember, a is negative, so, which it better be. This is negative V naught squared. Sorry, I should really put numbers in. 12 squared over 2 times a negative 22. The distance had better be positive, because how could it have a negative unless it slid backwards or something? So 12 times 12 is 144. And if I divide that by 44, I get 3.273 meters. Okay, so X final, or better yet, delta X is X final minus X initial, is 3.273 minus 0. Okay, and remember what we said about being able to analyze this as a real world problem? That's a little bit more than, that's about 10 feet. And 22 meters per second is almost 50 miles an hour. So a truck hitting its brakes, 12 meters per second is almost 30 miles per hour. Truck hits its brakes and stops in half of a second, still travels almost 10 feet, okay? Half of a second is an awesome reaction time to stop if you saw something come out in front of you. But you're still going to slide 10 feet in that stopping distance. Keep that in mind. These numbers I made up, but if you were to look at them and figure out what the deceleration of your car is, your car will slide quite a bit. And it's why if you're driving on like city streets and driving through town, just keep in mind that even though your reaction time can be fast, you're still going to slide a certain distance as you stop. And you might want to think about that. Or when you're getting ready to cross the street and you think cars can stop in time, they might not be able to stop in time. Their reaction times will be, but they could still slide into you. So this is kind of an interesting problem from that aspect. For a problem solving, it's interesting because we have a negative acceleration and we have a problem where we came to rest instead of starting from rest. Other than that, it's the same algorithm. Kind of draw it and understand what it's saying to you, write your variables, and then look for the equations that you need to solve. This problem also has quite a bit of what I would say is assumptions. You have to be able to read coming to rest means V final is 0. You need to understand that deceleration means that the acceleration is negative. Other than that, I think it's pretty simple, but it can throw you for a loop the first time. You can mess this up pretty easily with a sign error or two. So the following problem is our first problem where we have to divide things up into 2. Here we have a bicyclist. She accelerates from rest, constant acceleration from rest of 14 meters per second for 10 seconds. She then slams on her pedals, meaning she brakes, and decelerates at 28 meters per second squared until she comes to rest. What was the total distance she traveled, and how long did the entire trip take? So now we really need to divide this up into 2 separate problems. Even though we're going to have to take the time of both, we'll talk about that in a minute. But in the first, she starts from rest, right? So V initial is 0, and she accelerates for 10 seconds, where A is 14 meters per second squared. In the second, she comes to stop, and A is actually going the other way, so it's negative 28 meters per second squared. And V final here is 0. But we don't know what V final is, and we don't know what V initial is for part 2. These 2 things will be the same. Whatever her speed is at the end of this 10 seconds, that is her initial speed during the braking, right? We also don't know what x final is here, and we don't know what x initial is here. X initial here is 0. So we don't know how far she went, and then wherever she is here, that's where we start for part 2. So let's start with just the first part. We're just going to do part 1. In part 1, we have x naught, x final, v naught, v final, a, and t. And actually, I want to call this t1 because we want to know how long did the entire trip take. We want to know the total time. And the total time is going to be the time of 1 plus the time of 2. And then we also want to know the total distance. And that we can find pretty easily by, I'll show you that. But this time 1 and time 2, we may have to do some tricks to get the total time. Just because we can carry through the x final, we're only going to use one time. And if we used a time initial and a time final, then we'd have to have a time initial and a time final in the second part. I don't want to do that. I'll just add T1 and T2 together. You'll see that in a second. So for part 1 only, x initial was 0. I don't know what x final is. V initial was 0. I don't know what v final is. A initial is 14 meters per second squared, and T1 is 10 seconds. So here, I just want to fill these two things in. So I want to know how far she traveled, and I want to know what her v final is. I know that I have v initial plus AT is my v final equation. This is really simple because v initial was 0, and this was 14, and this was 10 seconds. So this is 140 meters per second. That part's super simple. How far did she travel? Well, x final minus x initial is equal to v naught t plus AT squared over 2. This is 0. This is 0. So my x final is 14 divided by 2 times 10 squared. This is 700. She traveled 700 meters. It's 10 times 10 is 100 times 14 divided by 2 is 700. So I know that. So I know what these values are for part 1. And now I want to find how much further she travels coming to rest and how much longer it takes. So let's do part 2. We're going to remember that x final for part 1 was 700 meters, and that v final for part 1 was 140 meters per second, which is extremely fast and stupid and yeah, not realistic at all. But that's okay. And T1 was 10 seconds. And remember that I want x total and I want T total. Okay, so for the second part, x initial, x final, v initial, v final, A, and T. Remember in the second part, she's braking, she's decelerating at 28 meters per second. Just like in the problem before, we write that. We're going to say that x initial is 700 meters. In part 2, she is at 700 meters at the start of it. That's how far she traveled in part 1. I don't know what x final is. Her v initial is the v final from part 1, 140 meters per second. And v final, I know is 0 because she comes to rest. She's braking to a stop, and I don't know what T2 is. So I either need to find x final or I need to find T2. Let's find T2 first. V final is v initial plus AT. V final is 0, and therefore I get v initial is AT with a minus sign because I move AT over, or T is v initial over minus A. V naught is 140 meters per second, and negative A is negative, negative, which is 28 meters per second squared. Time had better be positive. This is also T2, by the way, I should note. So what is 140 divided by 28? 140 divided by 28 is 5 seconds. This took all of 5 seconds. So what is our time total? Our total time What was it for part one? 10 seconds? So our total time is t1 plus t2, which is 10 plus 5, which is 15 seconds. The entire thing took her 15 seconds. And what will her final distance be? And here you can do it any number of ways. I'm going to use my friend, this one, 2a x final minus x initial. And I'm solving this for x final. So if I divide through by 2a, noting that v final is 0, and then that will cancel these, and then I need to add the x initial there. So x final is negative v naught squared over 2a plus x initial, which is minus 140 squared over minus 2 times negative, I'm sorry, I already picked up that negative sign. That's negative 28 is a, plus 700. And this is going to equal 140 times 140 divided by 56 is 350 plus 700. It's 1000 or 1050 meters. That's her final. So the total distance is 1015 meters. Okay, does that make sense? Yeah. Basically, she decelerated at double the deceleration of her initial acceleration. So it took her half the time and half the distance to stop, which is fine. It took her, like I said, half the time because she doubled her acceleration. That's pretty obvious. You could have done this a lot of ways. I'm not going to do them all the various ways. I want to move on. But the big takeaway here was we had to divide the problem up into 2 distinct regions. And then we had to take region 1 and relate it to region 2 to get the answers we wanted. Pretty simple, but I believe there's a homework problem much like this. And it may have a constant velocity section in the middle of it, right? But essentially, if you do the same algorithm every time, write down the variables, figure out what they are, figure out what the problem's telling you, solve the equations, and then for the second step, you're going to use equations or variables that you solved for from the first step in the second step. Part 2. Not too bad. Here, this is probably the most important problem we're going to do today. This problem is actually exactly what projectile motion is, and you'll see that in a minute. But what I have here basically is I have a car, or I have a truck, and the truck's going north. And by the way, I'm going to call this my positive direction. So I have a truck, and that truck's heading north with constant v, okay? And then I have a car up here that starts at rest and accelerates until they cross paths. And they are initially 200 meters away from each other, okay? So the car has acceleration, but no initial velocity. Acceleration is 13 meters per second squared. Is it positive or negative? It's negative because the car is heading down, and I decided that up would be positive. I could have down be positive, that's perfectly fine. But if I do have down being positive, V is going to be, this is V of the truck, by the way, V would be negative. I don't want to get into that, but essentially you need to remember the acceleration and the velocity of the car will be negative. Its position will always be positive, although it will be decreasing, because we're going to call this x is equal to 0, and we're going to call this x is equal to 200 meters. And what we want to know is at some point they're going to cross paths. We don't know where, we don't know when. We're going to find out when. So one car starting from rest and accelerating with constant acceleration, one truck moving with constant velocity and no acceleration. When do they meet? So how we do this is we write for the car and we write for the truck, we write their variables. X initial, X final. V initial, V final, A of car, T. And I should really denote these with a little C. X initial, X final, V naught of truck, which is equal to V final of truck, which is just V of truck, just to save time, A of truck, and T. The first one's easy. Again, constant velocity means that the truck is moving at 32 meters per second at all times and has no acceleration. I also want it to start initially at 0. The car, on the other hand, is initially going to start at 200 meters. The initial velocity of the car is 0. When we read through this problem, initially, at the same initial time, a car starts traveling south from rest with constant acceleration of 13. But remember, that's a negative 13 meters per second squared. I don't know what V final is. I don't know what X final is. I don't know what X final for the truck is, or T. But here's the thing that you have to know. The car and the truck are going to arrive at the same position at the same time. Therefore, the car's X final and the truck's X final are equal. And the car's time and the truck's time are equal. And that's the key to solving this problem, is I'm going to have equations for the car and equations for the truck. And I will be able to relate them by X final because it's the same, okay? So I want to know when, what position they'll be at, and what time they'll be at. So let's move to part 2. So in part 2, what we're going to do is write down the equations of motion. We want time and we want X final. Now for the car has acceleration. I could choose V final is V initial plus AT. I don't want to do that. For the car, what I want to write, it's X final minus X initial is equal to, of the car, is equal to V naught of the car times T plus A T squared over 2 of the car. We know that these two things are the same and they both appear here. And so we'll talk about that. Now for the truck, X final for the truck, same, minus X initial of the truck is equal to V initial of the truck times time plus A of the truck, but A of the truck's 0. So I'm gonna leave that alone. This was 0 for the truck, okay? And this is a number. So what I can do here is I know that this is, I'm gonna plug in some numbers, 200 for the car, and the car was initially going, was initially at rest, is AT squared over 2, or X final is equal to AT squared over 2 plus 200. But I know that X final here for the truck is equal to the truck speed of 32 meters per second times T. So this is equal to 32 times T. And if you look at this, what you see here is that we have, what was A for the car? 13. So this is really, if I move this over, I can set this equal to 0. So I have 0 is equal to 13 divided by 2. That's the car's acceleration with a minus sign, times T squared plus minus 32T. All I did was move that over, and so if I subtract 32T from both sides, I get a 0, right? Plus 200. And you can see here, this is A, B, and C of a quadratic. You're going to solve the quadratic for time, okay? And remember that the quadratic is B squared minus 4AC over 2A. When I do this, I'm just going to tell you right now that what I get is I get 32 plus or minus 32 squared minus 4 times A times C, which is 26 times 200, which is 5,200. It's a plus sign because there's a minus sign and A is also negative. So this becomes 5,200 over 2 times a, which is minus 13. And that's important. There's a minus sign on b, but there's a minus sign up front, and this b is squared, so I left it off. What this turns out to be is 32 times 32 plus 5,200 is 6,224. Square root of that answer is 79, basically. So this becomes 32 plus or minus 79 divided by 13. And remember, what this is going to give us is the time. So this can be one of two answers with a minus, If I use the minus sign, I'm going to get negative 47 over negative 13. And it'll be positive. If I use the plus sign, I'm going to get 112 over negative 13. I'm going to get a negative. So I need to use the negative sign. So this is 32 minus 79 over minus 13, which gives me 32 minus 79 divided by negative 13, 3.615 seconds. Okay. Once I have that, we're essentially done, because we can use the time for the car. So, or I'm sorry, the position for the truck was the velocity of the truck times time. And since it was 0, this will be where they meet. If I put the velocity of the truck was 32, so 32 times 3.6165, that gives me 115.6 meters. 115.6 meters. Okay. You can do this problem where solve this for t and plug that in, and you'll get a quadratic for x final. And then you could solve that for x final, and you would choose the appropriate one. You get 115.6 meters is where they meet. And then you could solve, knowing that and the velocity, you could solve for the time. I'm not going to do that. That's a lot of work. But it's the other way to do this. So the whole point of this is that you have two different objects with two different equations of motion, a lot more than two actually, but with a different set of equations of motion. But those equations are related by their final position and their time. And in projectile motion, the x and y coordinates are related by time. So you do this same thing in projectile motion. You take the y motion and the x motion, you treat them separately, but they're linked. The equations for them are linked. And what that allows you to do is, even though I have 3 variables missing, even though I'm missing some variables here, I can substitute in something I do know to solve an equation. To eliminate variables, I can substitute in x final or t, or I should say the equations for the truck solved for x final or t into the car equation to give me an answer, which is what I did here. This was the truck equation. I solved it for x final, and I plugged that in there, and it gave me a quadratic. It will often give you a quadratic. If you don't like quadratics, I'm sorry. That's why we reviewed it in math skills, because we ended up needing it. There may be one of you or more than one of you in class that can solve this without the quadratic, and that's fine too, if you can. I'm probably overlooking something. It's late. I've been doing physics all day, and my brain just wants to solve these problems in the easiest way without taxing myself. So, but if you can find another set of equations that gets you there, great. The idea is going to be, though, that you need to use the equations for one thing and the equations for the other and combine them to get answers, to eliminate variables, to eliminate unknowns. So we're on to the last part, and that's free fall. And free fall is really one-dimensional projectile motion. It's projectile motion when we have no x motion. So in free fall, you have a couple different cases. You can have something that you drop, v initial is 0, and you're at some y initial is h, some max height. You can have something that you drop with initial velocity, right? And then you can have something that you throw up from a height of 0 and it lands at a height of 0. And then you can have something that perhaps you start at a given height, a height that's not the same. We're going to do these same types of things when we do projectile motion, but generally these are the 4 cases that we're going to talk about. And the first thing we need to talk about is we're going to assume that y is positive upward. We're going to assume that the ground is always y is equal to 0. It makes it easier. And we're going to assume that whenever y is a maximum, we're going to call that h in my solutions. That means the maximum height, h max. If you throw it up, the greatest height it reaches. There's one thing you do need to know, one added thing. When something goes up and comes back down under gravity, at the very top of its motion, its velocity is 0 at maximum height. Its acceleration is still what we're going to talk about in a minute, but it still has acceleration. But what happens is it's got an initial velocity that's positive, that gets less and less and less, becomes 0, and the velocity becomes negative. So as it falls, if it's heading toward the ground, its velocity is negative because we chose y to be positive upward. As it goes up, its velocity is positive. The last thing we need to talk about is the acceleration. And the acceleration is the acceleration of gravity, which is 9.81 meters per second squared. And for now, we're going to note that that goes down, but we're going to write a is negative g, okay? And so what happens is we get those same equations from before, except now they're in y. And instead of a, we have negative g. And we have y final minus y initial is v naught of y times t minus g t squared over 2. And we have y final minus y initial is v final y plus v initial over 2 times t. And finally, v final y squared minus v initial y squared is equal to 2 minus g y final minus y initial. Okay, those were given earlier. Now, unlike constant acceleration, I'm going to ask you to draw a free body diagram for these problems. And the reason is that you need to be able to label y initial and y final correctly. And so the first few times you do this, I really, really, really want you to label things. And we're going to do that as we go. The first problem is going to be one that falls to the ground. And what I mean is I want you to label it ends up at the ground. It's initially at a height, which is given. And sometimes we're going to divide things up into 2 sections. I want you to draw that. And I want you to draw that the acceleration is g. It's negative because it's down. But for now, that's what I mean by a free body diagram on this. It's not really a free body diagram. We'll talk about those when we do chapter 5 and 6 next week, but it's close, okay? As I talked about, these are the things you need to know for projectile motion, one-dimensional free fall. These are our equations. They're exactly the same. The only thing that's being substituted is x for y or y for x, and a becomes negative g. Okay, so first problem I want to give you, you're up on your roof, and your roof is 4 meters, approximately 13 feet high. You fall off your roof, meaning you fall from rest off your roof. I want to know how fast you're going right before you hit the ground. Why right before you hit the ground? Because once you hit the ground, there's forces of the ground and blah, blah, blah. So we always say right before you hit. So right before you hit, and I want to know how long it takes you to fall off your roof, which may sound fun, but again, we're talking about rest, and we do the same thing that we just got done doing with all these constant Excel problems. And that is, we're going to write down our variables, y initial, y final, v initial, v final, a, and t. And you're going to get annoyed at writing a. I understand that. But for now, just write negative g or negative 9.81 meters per second squared. So in our picture, we know that y final is 0, and we know that y initial is 4 meters, and we know that v initial is 0, and we know that a is g, and that's all we need to write down. We want to find v final, so v initial is positive 4 meters, v final is 0, you're falling down. V initial is 0, I'm sorry, y final is 0. V final, I don't know, I want to solve it, and t I want to solve. So again, we can go to look at the equations, but I will tell you, we've been using v final is equal to v naught minus gt. We don't have v final, and that should tell us, if we go all the way back to these, where did we do this? The doesn't have. The only equation that doesn't have v final is that top one. So let's head back to our free fall. We have y final minus y initial is v naught t minus gt squared over 2. We know this is 0. You started from rest. And we know v final is 0. So what that gives us is y initial is minus g t squared over 2. We can solve this for t. T is the square root 2 y naught over g. The negative signs cancel. If I multiply both sides by 2 and divide both sides by negative g, and then I take the square root. So this is the square root of 2 times 4 is 8 over 9.81. And that answer is, how long do you think it takes to fall off your roof? 0.9 seconds. And once you have that time, I'm going to come up here. V final is V initial minus GT. This is 0. G is negative 9.81, 0.9. Note V final will be negative, as it should be. This is 8.86. 8.86 meters per second. That is pretty fast. That's, remember, we're multiplying that by 2.2 to get miles per hour. That's like 17 miles per hour that you hit the ground. Do you want a car hitting you at 17 miles an hour? Probably not. Falling off your roof hurts. Be careful. And you could try this by tossing a ball up there and letting it come back down. See how long it takes to fall. Time it on your phone. See if it only takes 0.9 seconds to fall from rest off your roof, essentially. Yeah, so you probably have experience falling off a roof. It hurts. It hurts you. That's why you get injured. But yeah. So here's another problem. And in this problem, we're standing on a bridge, an unknown height. So this is like falling off your roof if you didn't know how far your roof was, how high your roof was. So you're on a bridge over a river and you throw a ball straight down with some initial velocity. So now we also aren't starting from rest. We have initial velocity. But this velocity is down. And remember, we're always going to say y is positive up. That means that this velocity is negative. And we're given that 3 seconds after it leaves your hand, it hits the water. So how tall is the bridge? Meaning, where did the ball leave your hand above the water? And then what is the velocity of the ball right before it strikes the water? We always want to know that. It's useful. So what we have here is, again, now we're going to say y final is 0 at the water, and y initial is unknown. It's at the height of the bridge. We know that v initial is minus 33 meters per second, and we know that time is 3 seconds. And we know, again, that g is down and y is positive up. It's useful to always put that. So y initial, y final, v initial, v final, a and t, and again, minus g. We know this is 0. We don't know any of this other stuff. We know that time is 3 seconds. So we don't, we know this is negative 33. So we do know enough. I'm going to say maybe we don't know enough. So what do you want to solve first? Y naught or v final? Well, It's really up to you. I'm going to solve V final because it's fastest. V final is V initial minus GT. And we know G, we know T, we know V initial. So this is minus 33 minus 9.81 times 3. And that gives us 3 times 9.81 plus 33 is minus 62.43 meters per second. Once we know this, we have V final squared minus V initial squared is equal to minus 2G Y final minus Y initial. We know this is 0. If we divide through by negative 2G, okay, we then have negative Y initial. Multiply through by a negative. So what we get is we get that Y initial is V final squared minus V initial squared over 2G. And it's positive. It should be positive. V final was negative 62.43, and we're squaring that, minus 33 squared over 2 times 9.81. So what do we get? 62.43 times 62.43 minus 33 times 33 is 2808 divided by 2 times 9.81 gives me 143 meters. So my height, my initial height is 143 meters high. Does that make sense? So how long would it fall? As a way to check, how long would it fall if Y initial was 143? We would have Y final minus Y initial is V naught T minus G T squared over 2. Or we have V final squared minus V initial squared is equal to minus 2G Y final minus Y initial. Trying to think of if there's a fast way I can check this to make sure I'm right. I'm going to assume I'm right. It's going pretty fast, so initially I'm assuming I'm right. I don't want to waste any more time doing that. Anyway, so this problem was a little bit weird because we're starting with a negative velocity and we don't know height. And a lot of times we're given height, but in this problem we weren't. And in this problem, it was easier to find the final velocity and then find the height. I'm really hoping that I did this right. I believe I did. I'm a little worried. Something feels off, and usually when that's the case, I've made a mistake somewhere that my brain's trying to tell me I did, and I just don't see it. But anyway, so the next problem is a soccer ball launched upward, okay? And this is one of our final two problems. So a soccer ball is kicked straight up from the ground with an initial velocity of 40 meters per second. The ground is y is equal to 0. What's the maximum height that reaches? How many seconds does it take to reach that maximum height? What is its velocity before it comes back to the ground? And how many seconds is it in the air total? So this thing goes from the ground, it shoots all the way up and comes back down. And we're going to actually divide this up into two motions. The motion when it comes up to maximum height and the motion when it falls back down. This I'm going to call part 1. So here we know V initial was 40 and it's positive because we're saying y is up and y is 0 initially, and here y final will be 0 and y initial here will be h, y final here will be h. V final here is 0 at the top of the motion. So V initial part 2 will be 0 and V final will be unknown. And then we're going to need to find the time. We're going to need to find what is h, and we're going to need to find the time up and then the time down. This is our free body diagram. We write G is down, Y positive is up. So Y initial y final, v initial, v final, a, and t. So y initial is 0. I don't know what this is, but I'm going to put h. V initial was 40 meters per second. V final is 0 when it reaches maximum height. Remember, I'm only doing half the motion. Minus 9.81 or g if you want. And time, I don't know, but I want to find. I want to find h and I want to find t. T is easy to find at maximum height because we know that v final is 0 at maximum height. So v final is v initial minus gt, but this is 0. So v initial is gt, or t is v initial over g. This is really extremely important to remember. I'm going to show you something important in a minute with it. So 40 divided by 9.81 is 4.07 seconds. So it's up in the air for about 4.077 seconds. How high did it go now? Now that I know the time, I can do y final minus y initial is v naught t minus gt squared over 2, with y initial being 0 and y final being h. If I plug these numbers in, so 4.077 times 40 minus 9.81 times 0.5 times 4.077 times 4.077, I get 81.55 meters, which is really high. I guess an initial velocity of 40 meters per second, it would go pretty high up there, which is pretty crazy. Yeah, but apparently true, unless I've messed something up, which I don't think I have. That would be about 16 times 5, which would be 50, 80, and v naught times t would be 160. Yeah, it would launch to about 81 meters, 240 feet up, almost 100 yards straight up. That's pretty insane. Okay, so we found maximum height, and we found how much time it took to go up. So now, though, we wanted to know how long does it take to go down, and how many seconds is it in the air total? And so we can do a couple things here. So in part 2, we're falling from rest. So v initial is 0. Y initial is our maximum height of 81.55 meters. We don't know what v final is. Y final is 0, okay? And we want to know the time. So g, y positive up, right? So we have y initial, y final. Remember, this is part 2. V initial, v final, a, and t. And let's call this t2. Y initial here is our h. Y final is our 0 because it comes back to the ground. V initial is 0. It starts at the top of the motion and falls just like free fall. And v final, we don't know. A is negative 9.81 meters per second squared. We know that v final needs to be negative. So what can we do? We know v final squared minus v initial squared is minus 2g y final minus y initial, and this is 0. So this is 2g y initial, or h. V final squared minus v initial squared, but this is 0. So v final is square root of 2g y initial, which is 2 times g times h, is 2 times 9.81 times 8.155. Square root of that is what? Something went weird. So 2 times 9.81 times 1.55. Square root of 1600 is negative, positive or negative. We're going to go with negative. We know it needs to be negative because it's falling. Negative 40 meters per second. Now notice something. This is super important. It was initially launched. When it left the ground, it was doing 40 meters per second. When it hits the ground, it's going to be doing 40 meters per second, negative. But the magnitude of its velocity is still going to be 40. Why? Because it's subject to constant acceleration. It goes up, and the time it takes to go up is the time it takes to slow down from 40 to 0. And then it takes the same amount of time, or distance, time and distance, to speed up to 40 meters per second on the way down. That's only true, so V final is equal to V initial only if Y final is equal to Y initial. And how do you know that? Well, you know that because for the entire problem, if we do the entire problem, Y final and Y initial are 0. We plug this equation in for the full problem, that becomes 0, and that means that V final is equal to V initial. This whole side becomes 0. So you know that V final is equal to V initial on level ground when it's launched from Y is equal to 0 and it lands at Y is equal to 0. That is true. Secondly, the time to fall. So how long does it take to fall? Y final minus Y initial is equal to V naught t minus gt squared over 2. This is again 0. Our Y final is 0. The negative sign cancels, and we get g t squared over 2, or t is 2 y naught over g, which is another way of saying 2h over g, which was exactly the time that we saw. Well, I guess we didn't see it here. We could have seen it here. The time here was v naught over g. Anyway, let me see if I can figure out something here. I wanted in terms of y naught. Oh, right, I wanted in terms of h. So if I have y naught minus y final, nope. I have y final minus y initial is equal to yeah, I know how to do it. Okay. All right, you've decided to be a pain. Fine, okay. So what we have is we have v final squared minus v initial squared is equal to minus 2g y final minus y initial. Here this was 0, this is h, this was 0, so what we got was that v initial is square root of 2gh, and if that's true, if v initial is equal to gt, if I square this, if I square both sides, so squaring this, and that's equal to v naught squared is 2gh, that's equal to 2gh, divide through by g squared, and you get that t squared is 2h over g, take the square root, and you get what we see here, that the time down and the time up are equal. A better way to show this that I was trying to do is if we do the full time, okay? So again, y final minus y initial is equal to v naught t minus gt squared over 2. So this becomes 0 if it starts and ends at level ground. And so what we see here is that we get v naught t is equal to gt squared over 2, or that the total time, which is what this is equal to 2 v naught over g, okay? And if we go back to here, we see that the time up was v naught over g, but the total time So the total time is the time up plus the time down. And if the time up is v naught over g, and the total time is 2 v naught over g, then the time down had better be v naught over g as well. And we've already shown here that v naught is equivalent to square root of g over h. So essentially, we've basically shown this. What I'm trying to say, and I'm sorry, it's late and I'm losing my thread a little bit, but what I'm trying to say is basically this. Whenever you have either projectile motion or one-dimensional free fall, meaning you launch it, if y initial is equal to y final, all of your equations that feature y final minus y initial, that's all zero. So they all end up being zero. So zero is v naught of t minus gt squared over 2. And v final squared minus v initial squared is equal to zero. Anywhere, and zero is equal to v final plus v initial over 2 times t. Anywhere that you have that, you see that what you get is much simplified equations. And then when you combine that up with the fact that at the top, the velocity is zero, you see quite easily that the time up is equal to the time down, and the total time is twice either the time up or twice the time down. So if you know the total time, which is easy to find from here, you know that the time to go up is half that. This only works though, it only works when you're on level ground, when you start and end at the same y value, okay? Otherwise it doesn't work. It only works for these problems. But you can prove that to yourself by breaking the problem up into a problem where a ball goes up to the top or a ball falls from the top to the ground. And you can see that the times will be the same going up and the same going down. And you'll see that the velocity going up is initially the same as the final velocity when it hits the ground again. That's a consequence of constant acceleration, being gravity. In real life, that's not true because you have air resistance and you have other things happening, other forces at play. But if air resistance wasn't there, we would get that. That would happen. All right. One thing here, you're standing at the edge of a building, 12 meters above the ground. You toss the ball from the edge with an initial velocity of 5 meters per second. Maximum height it reaches, how many seconds does it take to reach the ground? What is its final velocity? So in this problem, I'm assuming that you're standing on the edge of a building and you throw a ball up. And the point here is that now y initial is going to be 5 meters and y final will be 0. So we can't assume that the total time is double the time up. That's all. And these problems, y initial, y final, v initial, v final, a and t, we need to split them up into 2 parts again. So part 1 is when it reaches maximum height, and y initial is 5. This is y is positive. V final at the top is 0. Y final at the top is h. That's all we have. So this is 5. Y final is h, and we're going to solve for that. V initial was, oh, I'm sorry, 12. This is 12, and V initial is 5 meters per second. 12 meters, and V initial was 5 meters per second. 12 meters, V initial was 5 meters per second. Minus 9.81 meters per second squared. V final is 0, and time I don't know. What we're asked to find is the maximum height above the ground, That means that while we could say that y initial is 0, if we do that, our height will be off by 12. So we have to use that y initial is 12. That will give us the right height above the ground, and you'll see that. And then how many seconds does it take to reach the ground, not maximum height? How or what is the final velocity before it hits the ground, okay? That's going to bring up a key point. So maximum height. How much time does it take to reach, or I'm sorry, what is the maximum height it's going to reach? We have all this. We don't have time, so let's not use time. So v final squared minus v initial squared is minus 2g y final minus y initial. Remember, y final is h. This is, sorry, not 0, but this is 0. And so what we get is we get minus v naught squared over minus 2g is y final minus y initial. And we're solving for y final. Y final is v naught squared over 2g plus y naught. And this is 25 over 2 times 9.81 plus 12. That is 25 divided by 2 times 9.81 plus 12. That's only 13.27. So it barely goes up a meter. And of course it barely goes up a meter because you only threw it at a velocity of 5 meters per second and gravity's pulling it down immediately. So it's barely able to travel before its speed is completely stopped by the acceleration of gravity, or deceleration of gravity in this case, and then it's going to start falling. So we know the maximum height. And here is why I had you find it. So now what we want to know is we know this is y initial is 12 and v initial here is 5. Now you could do this as 2 problems. A problem from this initial height up and then a problem down, if you want. That's perfectly valid. And here, y initial would be 13.27 meters, and v initial would be 0 because v final at the top was 0, all that good stuff. But it's actually, I think, faster to do the whole thing because we're asked for the whole time. So this was 12 and v initial was 5 meters per second. And this y final is 0, okay? And that's all we need. So we know that y initial is 12 and y final is 0 and v initial is 5, positive 5. Remember that a is still g and y is still positive up. Okay, v final, we don't know. We're going to find that in a minute. A is minus 9 point, minus g is fine. T. Okay, so we want total time. Okay, so we know v initial, and we know y final, y initial, and we know a. And so that should immediately tell us. Let's use this to find time. You might think, oh, I could use v final. Nope, you don't have v final. This is the only equation without v final. And unfortunately, this is a quadratic. Y final minus y initial, this is 0. So what I get is 0 is minus gt squared over 2 plus v naught t plus 12. Sorry, shouldn't do that. I'm doing that bad thing of plugging numbers in. So here's my A, here's my B, and here's my C. And my A is half of, my A is negative g over 2. My B is 5, and my C is 12. And I plug it into the quadratic equation. Remember, I'm solving for t here. It's the total time, all over 2a. So this becomes minus 5 plus or minus, under the square root is 25 minus 4 times g over 2, which is 2g times 12, so with a plus. So this would be 25 plus 2 times 9.81 times 12. That's 260. Take the square root, 16.138. So 260-ish, 260.44. Over 2 times a, which is really g. I'm just going to leave it at g for right now. This is minus 5 plus or minus 16.14 over 9.81. This is a negative because a is negative. Okay, Since it's negative and we're solving for time, we better get a positive time. If I did -5 plus 16.14 and then divided that by a negative, I would get a negative. So I need to do the subtraction. So -5 minus 16 is negative 21.14 over negative 9.81. And that gives me 21.14 divided by 9.81, 2.16, well, 2.155 seconds. And once I have that, I can just use B naught is, or B final is B naught minus GT. So this is 5 minus 9.81 times 2.155. 9.81 times the answer, and 5 minus this answer. This is minus 16.4. Minus 16.14, as it should be. It should be a minus because it's falling back to Earth, and we chose Y to be positive up. And that's it. That's how we do this problem. You can double check me and try and split it up into two problems, a problem where it goes up, and then change the variables at the top so that it's now free falling from rest, and see if you get the right answers. You should. The last thing I'm going to talk about, and this is really stuff that you need to kind of look at yourself. I don't need to guide you through this. Section 2.6 is all about interpreting graphs, and it's stuff we've already done. It's basically that when you have a B of t graph, right, and you have something like this, the area under the curve is the change in displacement, right? The area under a curve of an acceleration versus t graph gives the velocity. So what you can think of is A times t gives you v, and b times t gives you x, okay? And that's what the area is. It's this times this, like a rectangle. And in fact, if you have like 1 and 2, 1 second and 2 seconds, the integral from 1 to 2 of b dt is the area under this curve. Right side can be, yeah. Yeah, so go through that section in the book and make sure you understand it. That would give you the position, right? Because this would become v times t, right? Which would give you meters per second times second. It will give you meters. This integral will give you meters. So the slope of a graph gives you the change. The area under gives you the antiderivative, basically, which is what the integral is. Just look that up. It's really not that big of a deal, to be honest. I'm sure you saw it all before in calculus. So anyway, a lot of problems. I think some of them were fun. Falling off a roof is always fun. Seeing how long or how far it takes for a truck to stop is fun. But I also hope you got the algorithm out of it. I expect you to be able to do that on an exam. I'm going to ask you to do that. So part A is always what concepts apply. You'll see that it's a gimme. But question 2 on these problems is always list the variables, or draw some type of diagram or a combination of both. And then question 3 will be something like find the time, find the maximum height. Question 4 will be find the final velocity, okay? So that's how these work, and I need to see that you know the correct variables. That is a big part of solving these problems, is knowing the right variables and being able to find things like the initial velocity is 0 because it's at rest, or the acceleration is 0 because we're moving with constant velocity. Those things are important. They're as important as being able to do the math, okay? So we'll talk about that more later, but hopefully this gives you enough to be able to do your homework and understand this. This will lead into chapter 4, which is what we'll do Monday, which you might want to read over the weekend. Chapter 4 is projectile motion, and it's essentially this over and over again, except with the same object. It's an object that has both a motion in the y and a motion in the x, which makes it pretty easy. The other thing I will say, if you want to get a jump on your homework, is that for chapter 4, for some odd reason, they go back through averaging instantaneous velocity and position and displacement again. I know why they do it, but essentially all chapter 4 is projectile motion, and then a little bit of uniform circular motion, which is really easy, and then something called relative motion. And relative motion is really fun. It's not, I'm kidding. Read the stuff on relative motion, sections 6 and 7 of chapter 4. Circular motion is super simple at this point. We're going to do it 3 times, and we're going to add a little bit to it each time. And the first time we do it, super simple. But the relative motion stuff is a little weird, and we'll talk about it. So Monday will all be projectile motion and pretty much this relative motion stuff. Tomorrow, Thursday, you're going to have a lab to do. So anyway, I hope you're all staying healthy. I hope you're having fun. Hope this stuff is much more interesting than the math that we've been doing, because these are kind of fun problems. Do some practice problems. Do all these. Try them. Try to work at them and get them. Be okay with getting wrong. Anyway, I'll talk to you soon.